Okay, let's start. So glad to see you this morning again, and let's continue talking about this potential evaluation map, because really this is where the meat of these algorithms are. So again, we're really exploiting the fact that the solution operators more generally, and so initially we'll talk about this potential evaluation map where you're given a set of sources. So for a good while, we're going to talk about this geometry. So sources and targets. I'm going to talk mostly about Laplace, and then towards the end, I'll discuss the Helmholtz kernel, just mention what the differences are, what are most of the discussion we carry over. But there is this added complication that as the wavelength grows short, things behave a little bit differently. All right, so you recognize this from yesterday. So today I'm not going to talk so much about, we're not really going to talk about the analytic multipole expansions so much. We're going to try to generalize the discussion, talk about things in slightly more general terms. But just to connect, so this is the, so here's the problem formulated again. Yj are the source points, and xi are the target points. And now notice that we're working with a real kernel, the real valued kernel. So now the multiple expansion we're going to express in terms of sines and cosines. But this is really the only slide where I'm going to show it, because the exact form of the factors doesn't really matter for our discussion here. The key point is that this is a separation of variables. So you have a kernel that depends on both x and y. And I want to write it as something that depends only on x multiplied by something that depends only on y. Because then, in various sums and integrals, I can pull the x dependence out. Okay, so the caveat is that I cannot do it with a single term. But there's a rapidly convergent series. So second best. So this is what I mean when I say we're going to forget about multipoles. So I'm going to, just have these general functions b and c. And now I changed notation a little bit. So the multiple expansion has various idiosyncrasies. You typically start indexing at 0 and so on. Let's just forget about that. Let's start indexing at 1. And then we go up and keep k terms. So k will be the rank throughout most of the rest of the week. Right. So once you have a separation of variables, as we touched upon yesterday, this really corresponds to a matrix factorization in many ways. So evaluating A times, so Q here is the vector of source strength. We're multiplying it by the matrix A to get the vector of potentials F. Okay. So if you have this type of expression, so there was a couple of questions yesterday, so let's maybe do this explicitly. So we want to evaluate, I guess, the ith entry of AQ. This is sum now if I insert the separation of variables here, that's my notation. Now the point here, the key step is trying to change the summation order. Right, so now I move this sum inside, because it doesn't affect the x's, and then you get like this, right? So now this here is the pth term in the multipole expansion. And these formulas are precisely the formulas for the matrix-matrix multiply. So A is now expressed as the product of the matrices B and C. And we're often going to find it convenient to write this as commutative diagrams, like so. All right. So this is just a brief review of what we did yesterday. Now, let's think about matrix factorizations. So the big advantage of doing the multipole is that we have analytic expressions. So I know precisely in advance how to do this. And when you have analytic expressions, you know, it's very easy to design algorithms. So in the fast multiple method, if you recall, we had all these translation operators. And there's, you know, an explicit formula that tells you how to evaluate them. In particular, so the translation operators at the finest level, they of course depend on the exact given source locations. But once you've processed the leaves, you're done, right? So that after that, the translation operators depend only on the order of the expansion and on the relative centers of the two boxes that are talking to each other. Okay, but so the drawback to this is that it's not necessarily optimal. That potentially there exist better factorizations of this matrix. So we're given a matrix A, and what the analysis tells you is really an upper bound on its rank. Possibly its actual rank is lower. So what's the best possible expansion? And we're going to cycle back to the SVD many times in this talk. So there's this singular value decomposition, which can really be defined as the optimal rank K approximations. So the optimal rank 1 approximation is really the left singular vector U1 times the singular value sigma 1 and then times the transpose of the first right singular vector. You can take this as the definition of the singular vectors if you like. And then you can continue this process and you get a sequence of orthonormal vectors. These are the left singular vectors. These are the right singular vectors. And then here's the list of singular values. So we put this in a diagonal matrix. So I'm going to mostly assume that everybody knows this. I'm going to flash this slide many times during the talks because we're going to use it repeatedly in different contexts. But this is really the notation we're using. And then there's this well-known Eckert-Young theorem, which you know, precisely, you could take it as a definition, but as a theorem, it says that if you somehow define the singular value decomposition, then the optimal error, the minimal error in a rank K approximation is given by the next singular value, the first one you omit from the representation. This is if you use the spectral norm, and when you use the Frobenius norm, the minimal error is a little bit larger, but it's still given by the singular values that you leave out. And the best possible rank K approximation is given precisely by the first K terms in the singular value decomposition. So that's my definition of this: U sub K, D sub K, and V sub K. It's just the truncation of these matrices to include only the first K component. Okay. So now let's see how this works. So now we again have this matrix A, and the theoretically optimal factorization of it you get by computing its singular value decomposition. And you know, if you're in a situation where absolutely minimizing the ranks is critical, then this is what you should do. But it has various algorithmic drawbacks. So conversely to what I said about the advantages of the FMM, now we're in exactly the opposite situation. That if you're using the SVD, everything has to be evaluated, you know, numerically. For a given distribution of points, you just have to numerically compute all translation operators. And it really can be quite expensive. So this is not, for numerical work, this is not an ideal decomposition to work with. So we're going to introduce next a decomposition that's, in our applications, this is not always true, but in our applications, it's almost as good as a singular value decomposition, and it has a lot of the advantages of multipoles, in that we have more analytic expressions for handling things. So this is what I call an interpolative decomposition. It's very closely related to, so in linear algebra, there's this concept of rank revealing QR factorizations, and the two concepts are very closely related. So our work in this area has really been, it's sort of some minor observations. From a theoretical point of view, it's some minor observations on earlier work on rank revealing QR factorizations, but we're really using them in a fairly different way than what was done previously. So the interpolative decomposition, so given a matrix A, it looks like this. So the statement is that if the matrix A has rank precisely k, meaning that the remaining singular values are 0, then you can write A, you can always write this is a theorem. So you can always write A as a product of a matrix that contains k of the columns of A, which of course leaves the question, how do you pick them? This is merely an existence theorem. So you can pick k of the columns of A, and then you can express all the remaining columns of A using these k chosen ones as a basis. So if we have A, then the dimensions look like this. So this is, what do I call it? The skeleton. And then I have this matrix. So this is V star. And I will observe that V star must contain an identity matrix. Right. So suppose for simplicity that I can pick the first k columns of A. This is non-typical. This is just a temporary little crutch. But say that the first k columns of A span the column space. Then I have a k by k identity matrix up here. And then here I have a matrix which I'm going to call T. So T here is of size k times n minus k. Now, this is sort of, it's of course handy to have this kind of thing. But for it to be useful for numerical work, this matrix has to be reasonably well conditioned. So if you use a singular value decomposition, then the matrix that goes up here, it's as well conditioned as you can possibly have. It's an orthonormal matrix, so its condition number is 1. All its singular values are exactly 1. In this case, it's not quite as good, but it's good enough for most numerical work. So the statement here in the theorem, and this is the key part of the theorem, is that no entry of T has modulus larger than 1. And this turns out to put some bounds on the singular values, on the spectrum of the singular values for the matrix V star. And in order to do that, this is why we need to permute the columns of A. So in general, it's not the first k columns of A that form the good basis. The statement is simply that you can find k of the columns, so a subset of the index vector, that have this nice property, that they form a very well-conditioned basis for the column space. All right. So how do you compute this in practice? And this turns out to be a little subfield of computer science, arguing that it's actually a very hard problem. It's in some sense combinatorially hard. You have to more or less just try all selections of k, all draws of vector k long subset of the index vector 1 to n. But it turns out that from a practical point of view, this vastly overstates how hard the problem is. So there exists very rigorous bounds by Gu and Eisenstadt, saying that if you relax this condition very slightly, that the condition that no entry of V must have modulus larger than 1, if you accept them to be 1.1 or 2 or just a little bit more. So it's a classical situation. You have some sort of CSE type problem that is extremely hard. You relax it slightly and now it becomes computationally very feasible. All right. So if you do this slight relaxation, then there exist very strong algorithms. So algorithms that scale as worst as m times n squared, assuming that m is larger. more typically they scale as m times n times k, which is really as good as you can hope for a general matrix to produce a rank k approximation. Almost. I'll show you a better method later today that beats that, but that's sort of the normal best case bound for computing a rank k approximation. Okay, and then so something that we've been pushing, I mean, it's not a unique observation to us, but I think that it's very underappreciated, is that for the most part, you really don't need these rank revealing QR factorizations. That if you're just careful, then doing a classical QR factorization will give you really most of what you need. So the way that I always compute an interpolative decomposition is using some variation of classical Gram-Schmidt. So given this matrix A, what you do is you just look for the largest column, and it's a classical, very simple greedy algorithm. You look for the largest column. Okay, so I use this. So this will be my first basis vector. Once I pick that, I orthonormalize the remaining columns with respect to the first, then just pick the second largest. Move that one up front. Orthonormalize the remaining ones, and continue. So there's one slight caveat. So if you just do it the way it's written in the textbooks, then it looks as if this performs much worse than rank revealing QR. But it turns out that the only problem here is that numerically, even if you use modified Gram-Schmidt, which is supposed to be a fairly accurate algorithm, you lose orthonormality in the basis you're constructing. So you need to do a double reorthonormalization. So there's some links to papers on the website. I'll spare you the details, but the main message I want to convey now is that it's simple. Computing an interpolative decomposition, for the most part, is quite simple. Just do plain QR with a slight tweak to it, that you have to rigorously enforce orthonormalization as you go along. All right, so this is how you compute interpolative decomposition. And this works very well when the singular values decay rapidly. In our case, they do. They do. We know from the fast multiple method that expansion provides an upper bound for the ranks, so we know that the rank decays exponentially fast for these matrices. And in that case, it's almost indistinguishable. The accuracy you get from doing an interpolative decomposition compared to an SVD, it's extremely marginal. If the optimal rank is 23, then the ID will give you maybe 26 or something like this. Yes?
So does the Gram-Schmidt process satisfy the requirements on B, that they have to be within some bounds? I'm curious as to how that's enforced.
So it doesn't do it explicitly. So this is what Gu and Eisenstadt did. Okay. So they showed that you can cook up counterexamples where the classical Gram-Schmidt process does not produce a good ID. But so their trick is to have a little, you have a little check. And if the greedy algorithm does not produce a good algorithm, you go back and you swap out some columns and then continue. But Gu and Eisenstadt, and in the classical literature on rank revealing QR, they have very rigorous enforcements they want to enforce. So they want to accurately capture several singular values. Whereas in our applications, really the only thing we care about is the error. The overall error. Whether the 10th singular value of a scale is a good approximation to the 10th singular value of A, I don't care about so much. So we're relaxing the requirements a little bit. But yeah, if you do that, things work very well. Any other questions?
So here we use Gram-Schmidt. But Gram-Schmidt is not backwards stable. So is there anyone trying to use householder or something?
The householder works very well too. Yeah.
But here are we assuming A is well conditioned?
No. A is always heinously conditioned. Its largest singular value is basically 001. and they plunge down to machine precision, and then they stay at machine precision. Right. But I mean, okay, so we're not talking about classical Gram-Schmidt. It's first of all, it's modified. But then it's also modified with an additional reorthonormalization.
Question?
Yeah.
What's the metric for determining the maximum column of that?
Well, we're just looking at the L2 norms.
Okay.
Yeah. No, so again, for matrices whose singular values decay slowly, what I'm saying is the notion of doing IDs for matrices whose singular values decay slowly is quite complicated. That's a much nastier problem than what I'm looking at here. So for these matrices whose singular values decay exponentially, it turns out that there's not much of a difference. But the remainder term, let's go back and look at it. Okay, so this is the remainder term in the spectral norm. This is in the Frobenius norm. But if this is an exponentially decaying series, then it's really dominated by its first term. So there's not much of a difference between whether you measure the remainder in the Frobenius and the spectral norm, which simplifies numerical work tremendously. So we're exploiting the fact that we're looking at fairly special matrices here. Let's see, where are we? Okay, so this is what it looks like when you solve this problem with using the interpolative decomposition. So we're given a set of source locations, a set of target locations. Now each source location corresponds to a column of A. So physically, when I'm doing Gram-Schmidt on the columns, I'm picking the largest one. And what I'm doing then is that I'm really looking at which one of these locations sends the strongest signal to the targets. So it corresponds to picking one of the points. Notice that I'm doing it for a given geometry. I'm not doing it for a given vector Q. The processing is for a geometry, not for a specific vector. Right. So I pick the column that corresponds to really it's going to be in practice the source location that's the closest to the targets. That's the first one I pick. Then I orthonormalize everything with respect to that. So say I pick this guy as the first one. Then the next one I'm going to pick is not going to be this one, because the signal that the guy that's very close to it sends to the targets is very, very similar. So once I've orthonormalized, this one is going to be much less important. Okay. So I pick something else. And then you proceed, and at some point you notice that the remainder of the matrix, the residual, has norm that's less than the specified tolerance, and at that point I stop. So the result is this type of subselection of the points, and then the way I'm going to use this in numerical work is that if you give me a vector of source strings up here, there's this map V star, which notice what it does. So the V star contains a K by K identity matrix. So for the red dots, I leave the sources untouched that were given on them. But then I add a contribution from the gray dots. So the gray dots I'm going to drop. So the source strings on the gray dots have to be redistributed onto the red dots somehow. So this is my analogy of a multipole expansion. So it has the same function, although the way we do it in practice is very different. Right. So then once I've done this local computation, so I've mapped the sources on the gray dots onto the red dots, then I get this compact representation Q hat. And the main point here of all this is that then the second leg of the decomposition, going from sources to targets, so what I used to call, so I guess this is a translation operator, targets from outgoing, this is now just, it's a part of the original matrix. So I do this through the original kernel, that the sort of physics of the interaction is exactly the same as the physics of the original problem. So the potential I'm evaluating at the blue points is exactly the potential induced by a number of point sources at the red points. So this is This is the main advantage of using interpolative decompositions in this context. Okay, so I can do this symmetrically. I can hit the target points as well. So notice that if everything I said you can apply to the transpose of the matrix. So instead of picking columns, I pick rows. What this corresponds to physically is picking target locations. And then we get this sort of diagram. So this is the multipole expansion. So I evaluate sources Q hat, just as on the previous slide. Then the skeleton matrix now is it's a K by K submatrix of A that maps me to target locations here. So I evaluate the potentials on the blue points. And I use really an interpolation that says that I can reconstruct. So any potential induced by charges over here, if I know it's on the blue interpolation points, then I can accurately reconstruct it at all the points. All right, so here's a comparison. So the red dots is the accuracy you get from multipolar expansions. Notice how they come in pairs. So it's one sine and one cosine term. And you have to get both of them. If you have just one of them, it doesn't improve the error or anything. So you need both to get an improvement in the error. Yes?
Is what you're describing allow the source locations and the two locations, xi and yj, to be identical?
No, they have to be separate here. Yes. Yes. Otherwise, A will not have low rank. Otherwise, we have to use this hierarchical. You cut A up. Its off-diagonal blocks have low rank. And then you have to do this sort of multiple type hierarchical procedure. But what I'm doing now, the objective is to plug it into that kind of hierarchical procedure in a little bit. All right, so here's the upper bound. This is the multiple expansion. The blue dots are the lower bound. That's a singular value decomposition. That's the best you could possibly do. And the green ones are what you get from the ID. All right, so the first point to notice here is that the difference between the ID and the SVD is negligible from numerical point of view. It's, and it's cheaper to compute the ID than the SVD. So, why not use it? And here's, we showed this before. Oh, I didn't mention before that these skeletons I'm showing, they're computed to very high accuracy. These are not computations that are valid with, 1% error or something like this. This is 10 correct digits at least. All right, so one point is that the SVD and the ID are very comparable. But then the other thing that's interesting here is that the multiple expansion is really extremely suboptimal for this case. But I'm not being quite fair, right? Because the multiple expansion, so for the red box, the multiple expansion is valid at all these points. Whereas what I computed in the previous slide is really a directional expansion. So I computed an expansion that's really only good for evaluating potentials over here. What if I have potentials sort of all over the place? And what if I don't know the potential locations in advance? Can I still do a skeletonization of this box? And a priori, it looks a little hard, right? Because how could I possibly, in principle, would need to do an ID of an infinite matrix or something. But
so you made the comment that you can beat multipole because you're restricting the observers to be inside the target box. Is it also true that interpolation will be good sort of in the shadow region of the target box? Like
it
will.
Is it
also sort of range gated, if you will?
Yes. Yes.
Is it valid beyond the target in that direction or only inside the target box?
In practice, yes. It's not quite a mathematically rigorous statement, but we can fix it. We'll do something better. If you want to use it behind, then use this instead. That's what I'm going to describe now. All right. So the problem now is, so if I want to compute a skeleton for the red points that's valid at any possible observer point, then what do I need to do? Well, so first we're going to use potential theory again. So notice that any potential caused by sources inside the red boxes, it's going to be harmonic outside the small black box. And in particular, we're going to restrict the observer points to be outside the green square. Now, outside the green square is harmonic. And Moreover, it's very nice and smooth on the green square. And now there's a representation theorem that says that if I know the potential, so the potential outside the green square, it satisfies the Laplace equation and appropriate radiation conditions at infinity. So now if I know it's on the green square, then the Laplace equation has a unique solution. So then if I know it's on the green square, I know it's everywhere outside. I can, in principle, theoretically reconstruct it. I mean, there's even very easy in-school representations for it. So what this tells us is that if I can find a skeleton that's valid for mapping sources to potentials just on the green square, I'm fine. If I do that, I'm golden. Then I know from theory that necessarily I will correctly reconstruct potentials outside. Okay, and then the other observation is that since I know a priori that the function is very smooth on what was the green circle before, I only need to sample it reasonably finely. So you have to think a little bit about how finely, but in practice you don't need that many points, at least not for Laplace. All right, so all I need to do is compress the interaction between these target points and the source points. If I do that correctly, then the skeleton I get in the source region is necessarily going to be valid at all well-separated points. All right, so now you see it used to be that the rank was 20, but this was for a directional representation. Now when I do a more fair comparison with a multipole, I find that the rank is actually 45. Okay, so I'll compare in a moment how we're doing compared to the multipole expansion. But before we do that, there's one more critique. So in the computations that we did here, so now we've constructed a set of skeleton points that's valid everywhere outside. But still, these computations are idiosyncratic to the particular geometry that I'm given, the particular set of source locations inside the box. So in order to do a really fair comparison, we need to deal with that too. So what we're going to do is we're going to skeletonize the continuum operator. So in this case, now we do it for any source location, any source distribution Q inside the source box. We're going to map this to potentials at the target region. So now the target region is going to be this larger box, just the boundary of the larger box. And I'm going to compress that. And now I'm arguing, now I can do a fair comparison with a fast multipole expansion, just to see how we're doing in terms of optimality. So we'll start with doing two concentric circles to be maximally fair to the fast multipole method, because this is really the geometry that expansion is derived for. So, okay, so we take a bigger circle of 3 times the diameter of the inner circle. We skeletonize. These are the skeleton points we get. And now let's compare. All right. So the interpolative decomposition is the green line. So it's reasonably close to the singular values. So the singular values are the very optimal ones. But now something curious has happened. What happened to the multipoles? Let's zoom in. Those of you who sit in the back probably only see 2 lines here. Right. It is really only 2 lines. This is a mathematical theorem that for this particular geometry, the multipole expansion is the singular value decomposition of the continuum operator. So, an alternative definition of multipole expansions. Yeah?
You didn't really need to fill in the interior of the source domain in this case, right? Because there's also a representation theorem for the interior. You could have just put points in the boundary.
That's right.
Is there a deliberate choice there? It's just a totally complete something.
No, that's just a rhetorical point. It seemed clear to me. I considered both options. But I should mention that it's possible, yes. You can do the same maneuver. All right. So here's the outer boundary. I use this representation theorem to say I don't need to consider points out here. Likewise, I could have gone from the interior, eliminated the interior points, and have sources only here and targets only here. This is sometimes very useful. All right, so now let's squeeze the circles together a little bit. Let's make the ratio between the radii smaller. Then we can still skeletonize. This is what the skeleton looks like. And now this is what the expansions look like. So it's, because the overall picture is exactly the same as before. It's just that the decay is slower, precisely as theory predicts. One difference that happened is, what do you think happened here?
Is that due to discretization?
Yes. Yes. Sorry. I'd forgotten I put that on the slide. Right. So, yeah. So what's happening here is that I'm putting, this is for a finite resolution, right? So given the number of points I pick in the angular direction bounds the angular resolution. I can't resolve frequencies that are smaller than that. So this is something you have to think about. You have to, for all of this to work nicely, you have to sample finely enough. But this is just a very simple back of the envelope calculation. We'll give you, you can tabulate it because there are only, fixed number of geometries that we're considering. So it's something you have to think about a little bit, but it's really no real difficulty. Okay, so now let's go back to, so this is the geometry in the fast multiple method. We have a bigger box that has 3 times the side length of the inner box. And now this is the slide I've been building up towards. So here's the fair comparison between the fast multiple method, the SVD, and the interpolative decomposition. So the fast multiple method is the worst. It's an upper bound, but its big advantage is that it's an analytic expansion. I don't need to do any computations for that one. And it's doing very well. The difference is not that big. But then the IG and the SVD perform very similarly in this case. All right, but the ID has certain advantages over the fast multiple method. Now let's creep the outer boundary inside. So in the direct solvers, I'm going to push the blue box all the way into touch the inner box. So I need the outgoing expansions to be valid in a larger region. Okay, but so let's do just a little bit at first and see what happens. So here's the skeleton. Now I need 108 points. I used to only need 45 points. Here's the comparison. Now you see that the fast multiple method is, or the fast multiple, no, it's not fast anything. The multiple expansion is doing much worse, as you would expect. Because recall, so in this case, the outer one is really quite snug. And the fast multiple expansion, no, it's not fast. I cannot say multiple without saying fast first. Right. So it's valid outside this circle, right? And now the ratio between the smaller radius and the larger radius, it's really not that, they're not that different in this case. What if I push the outer box even closer? Let's see what happens then. Like this. Yes?
So you get a skeleton point inside, but using Hierarchical argument, technically we have all the skeleton points on the Hierarchical. Is it a numerical artifact that you get?
No. These numerics are done very carefully. So, what I'm doing here is, so here I have an underlying Chebyshev grid. So these functions are actually interpolation points. So they point to basis functions.
So why do you get the skeleton point inside?
Oh, so in order to make this a fair comparison, I'm actually correctly discretizing.
I think you're referring to previous chart.
Previous chart with this chart, after you skeletonize and you get the, yeah, those
If you went
internal,
to Oregon, there was one like right in the middle.
yeah,
Ah,
those internal points.
wow, it just turns out that this is
That's the way you do that.
advantageous. Yeah, so notice that, so I'm scaling by the quadrature weights here to faithfully, I have to scale the matrix so that the singular values of the matrix faithfully represent the singular values of the continuum operator. All right. If I didn't do that, then all the points would be out in the boundary. But the boundary nodes, so the Chebyshev, so in Clenshaw-Curtis, the quadrature weights go to 0 at the boundary. So this pushes the method against putting all the weights out in the boundary. And if you think about it, it's sort of, I mean, these are good interpolation points for functions, for, in this case, polynomials in the interior box. If you want to interpolate a polynomial, you don't want to put all the points on the boundary. So this is really, I'm really deliberately compressing the volume operator here. Right, okay, so let's look at this. Here are the skeleton points. Now I need 260. I started with 45, then it went up to 108. Now I need 260, but things still work. That's the fast multipole method. The multipole expansion, it does not converge. It starts to converge a little bit, but then it's a divergent series expansion. So in this case, you really need to do numerical compression. If you do numerical compression, everything works just fine. All right. And you can do, when you use these numerical compressions, you can also use, in many cases, you don't have general geometries, where you're compressing something like a boundary interval operator, where the points lie on a lower dimensional subset. And in that case, the ranks are better. So in this case, the rank is 25. It used to be, was it 45? If I had the entire box filled. So this is the kind of thing that you can exploit when you do numerically constructing the compressions. So this is again for the geometry with a little curve inside. So again, now the fast multiple method, the multiple expansion, it works, right? But it's an upper bound. It's suboptimal. And these are just some frivolous slides to show that you can compress all sorts of different geometries. In this case, if you try to do these expansions analytically, at least I would struggle a little bit on what to do. But numerically, it's very easy. You can put the boxes next to each other. You don't even need any buffering. It's the rank of interaction between these two boxes is 46 to 10 digits, even though they exactly touch. All right. So I believe so the main point here is really that when you use these skeletonizations or interpolative decompositions, the main advantage, I've touched on all these earlier, but the main advantage is that in the end, the interaction potential between your compressed representation of the sources and your compressed representation of potentials, it's really done via the original interaction kernel. That a scale here, its entries are really just samples of the log function, of the fundamental solution. All right, so let's discuss Helmholtz for just a few moments before closing this lecture. So first, just to review, or really just to introduce my notation. So we start with where does the Helmholtz equation come from? It typically comes from some sort of wave equation like this. V is the wave speed. Then you assume that the time dependence is harmonic. You plug that in, and then the second derivative with respect to time gets replaced by omega squared. So omega is the phase speed. Then you divide by V, and you get this Helmholtz parameter, kappa. So large kappa corresponds to high frequencies, corresponds to short wavelengths. So as kappa increases, things get more difficult, is the short story here. And then the other thing I wanted to mention is that once you consider free space problems, there's always something called a radiation condition like this, which distinguishes, make sure that, so in general solutions to the Helmholtz equation, consists of waves that are physically sort of outgoing and incoming. And you have to separate this somehow. So there's something called a radiation condition. Notice that now the potentials are complex valued as implicit by this assumption. So for the most part, especially when you talk about free space problems, we essentially always consider the unknown to be a complex valued function. And now the fundamental solution you can show is this Bessel function, H0. And other than that, the solution formula looks just like for Laplace. So for Laplace, we had log here. Now we have this Bessel function. Let's look at what its behavior is. So here's the real part and the imaginary part of H0. So notice the oscillations here. So these are all the solutions to wave equations. So they have to be oscillatory, right? Let's zoom in a little bit because this picture, I wanted to show you the oscillations. That means I don't really see what's going on at the origin, but this is important, so let's zoom in. So at the origin, the imaginary part goes to infinity of H0. And it behaves just like the fundamental solution of Laplace here. So once your waves at length scales that are sub-wavelength, it sort of, things really look like Laplace. So you have a log singularity at the origin. All right, now let's revisit. So this is the same geometry as I had on some slides yesterday. So we're putting, and it's the same slide as this geometry. You have sources in the domain omega s. You have targets in omega t. I see the source dots turned out a little small, but the geometry here is really just, I just randomly put down 5 source locations in the red box, just to show what do the solutions to the Helmholtz equation look like. So this is the solution for, so here the wavelength of the problem is about, so the red box is just a little under 1 wavelength. So you see there's radiating waves going out from these sources, and I had to truncate this. So these peaks, they really go to plus minus infinity. So there's some sort of nastiness in the red region. So the solution in the red region is a little unpleasant. Here we have this mild smoothing that I talked about yesterday. You gain 2 derivatives. You start with delta functions, and then you gain 2 derivatives in the solution, but that still is not particularly smooth. But the point is that we're really only going to evaluate the potential away from the sources. And over there, it's perfectly nice. It's a C infinity function again. And it's a reasonably simple function. So let's zoom in. So you see there's a little bit more. For Laplace, these things really look extremely simple. They're more or less flat. You know, if you do approximation by the piecewise linear, you're doing reasonably well. If you're adding a quadratic term, you're doing quite well. If you're adding, you know, just 1 or 2 more terms, you're visually indistinguishable from the exact solution. For Helmholtz, it's not quite that simple. There's a little bit more detail. And there's a little bit more detail in this regime where the wavelength is comparable to the box size. Now let's look at a shorter wavelength. So now I cranked up kappa a little bit just to show why do things get more complicated. So now the box here is about 6 wavelengths large. So it's still not, you know, it's not a massively small wavelength or anything. But I see it, it's a little hard to see on the computer screen. You can download the slides if you want to see this in detail. It's a little bit better once we zoom in. So you see now it looks like this. It's really a very oscillatory solution. So it's more complicated to represent these solutions. Right. This is the absolute value. So the absolute value does not oscillate in quite the same way. All right. But other than this issue of the oscillations, things work pretty much the same as for Laplace. So there exists a multipole expansion, so to speak, of the Helmholtz equation. It consists again, now the expansion functions are some sort of Bessel functions. And this is what the expansion looks like. And basically most of the equations of classical potential theory has this type of separation of variables. So, you know, there are these big tables of books that you can look all these things up in, and they specify precisely convergence rates and everything. And this is what you need if you want to build classical multiple methods for the different equations. Okay, but let's look at things numerically. So here's the same geometry as we had before. Now the inner box is about 1 wavelength. And this is what the skeleton points look like. Recall for Laplace in this case, we needed 45 skeleton points. For Helmholtz, we need 49. I guess these are actually complex variables. In some sense, maybe it's twice as many. But conceptually, things work the same. This is what the singular values look like. The blue ones are the singular values. The red ones are the multiple expansion. And the green ones is what you get when you do an ID on this problem. So conceptually, it looks very much like Laplace. Maybe it's a little bit slower the first couple terms. This is when the source box is about 1 wavelength. Now let's crank kappa up. Look at a smaller wavelength. And recall, so now I'm going to look at something like this, when there's much more detail in the solutions. What happens to the ranks in this case? Well, here's the skeleton. Now I need 118 points. So the rank has gone up substantially. And this is what the curve looks like. So for a long time, I have essentially no decay at all. Which means that, you know, as you add basis functions or as you add source locations, for a long time, it looks hopeless. You're not getting any improvement in accuracy. And then there's some point after which you start decaying. And this decay is actually typically faster than it is for Laplace. So once you resolve it, you're in good shape. Then everything looks exactly like Laplace. So you have to resolve the object in terms of wavelengths, and then after that, you have very strong smoothing. So this point up here, it's very well understood theoretically where this plunge happens. In a nutshell, it's really that you need to, it's precisely what I just said, you need to resolve your geometry up to the wavelength. So in 2D, this is really the diameter of the source region counted in wavelengths. That's when the plunge starts. So, and this is why designing a fast multiple method for the Helmholtz equation is very hard. So if your big computational box, say it's 100 wavelengths, then, and you have a lot of levels. So at the fine level, say you start with, you know, a quarter wavelength. Well, everything looks exactly like Laplace. Half wavelength, it looks like Laplace. 1 wavelength, it looks like Laplace. But then as the boxes start getting to like 2, 4, 8 wavelengths, if you were to use fixed length expansions, you would lose all accuracy. So what you have to do is you have to increase the expansion lengths on the higher levels. And if you do just a naive generalization of the fast multiple method, this will not go well for you. All right. So this is one complication of the Helmholtz problem, that we have to resolve everything that's above the wavelength. There's really no loss of information there. Then another problem that you have to think about a bit is that the Helmholtz problem is different from Laplace. So Laplace, under very, very mild conditions, the Laplace-Dirichlet problem is always well posed. You know, it has a solution, and the solution is unique. This is not the case for Helmholtz. So if we look at some box, omega, and just Dirichlet problem, then you will find that for certain values of kappa, this solution is ill-posed. There are functions f for which it does not have a solution, and it has, you can set f equal to 0, and it still exists solutions. So when does this happen? So this happens precisely when kappa square is an eigenvalue of the Laplace operator with 0 Dirichlet data. So this causes a number of complications in numerical work. So things like whenever So in these lectures, this trick of representing the far field by a finite domain, and some sort of what I'm going to call them proxy points in this finite domain. So these things are very simple for Laplace. When you do Helmholtz, you have to tweak them a little bit. I won't always mention this explicitly. I'll focus on Laplace in the lectures. But in various, when you look at other problems, there are usually some little tweak. So if this is the source region, then the set of proxy points in Helmholtz, there are various things you can do. So in order to resolve this, one thing you can do is that you look at both u and du dn on the boundary. If both the Dirichlet and the Neumann data is 0 on the boundary, then the internal problem is identically 0. So this is something you can do. You can look at not only the potential values on the proxy point, but you can also look at the normal derivatives out there. If you include both, then everything will work the same. Something else you can do is that you can put a second layer of proxy charges. If you prefer to just look at Dirichlet data, you can put a second layer out here, and then you need to separate them appropriately, maybe a quarter lambda or something like this. Because then, if the potential is 0 on both of these, if u is 0 on both of these lines and it satisfies the Helmholtz equation inside, then it is identically 0. So the possibility of resonances is something you have to keep in mind. It can really hurt you if you ignore it, but if you keep it in mind, there's usually a fix that costs you, that leads to some increase in cost. So Helmholtz is typically a bit more expensive than Laplace, but conceptually, usually most of what you're doing can be handled.
Yes. Do we have access to derivatives of the potential in the ID?
If we have access to
the derivatives and the gradients of the potential.
Yeah. Yeah, so again, it's so the way the ID represents a potential, okay, so here's a source box. So I start with a lot of points. I do an ID, only a few of them survive. And then I know everything about the potential in the far field. Because the potential out here is just the potential induced by point sources. So in Helmholtz, the fundamental solution is different, but otherwise it works exactly the same. So so out here, u of x is really just some sum up to the rank k. Okay, this is too small, nobody can see it. So the representation of, so if x is some point outside, that's well separated, then the potential at x is a sum over the k skeleton points. Then there are some qj hats. These are the modified charges. And then it really just looks like this, where G is the fundamental solution of the underlying problem. So you have this analytic representation, and now you can differentiate this. You can differentiate it 10 times if you want to. You have really all the information about the field out in the far field to your specified tolerance. And yeah, this is my last slide. Any other questions? Yes?
Does the, how does the number of proxy points that you need, or skeleton points, proxy points for these, in this case you're suggesting that we maybe need to double the number of proxy points to handle Helmholtz in a reliable way.
Mm-hmm.
Does that result in a doubling of much of the cost of the rest of the algorithm, or in practice it doesn't matter?
Yes, the compression step, computing the proxy points, that step gets more expensive.
Right.
But it typically does not change the number of skeleton points you actually pick.
Right.
So once you've done the compression, the rest of the computation Right? It's complex arithmetic instead of real if you're
Yeah.
doing Helmholtz. But other than that, it's, you know, it doesn't change things.